Welcome to the joint working group meeting with the particle number metric group and the sensitization test method group. I'm sorry, I'm adding people to the meeting, so I'm a little bit distracted. Mike McCawley is going to give a discussion talk about his experiences when he supported OSHA for the survey of facilities while they were determining what requirements they would implement for the Beryllium rule. So Mike is a distinguished scientist. He worked for NIOSH, I believe, for over 30 years. He was the principal researcher for the NIOSH studies on beryllium, as well as other studies. And he's also a renowned aerosol scientist and applied his techniques to the workplace and discovered actually what causes the beryllium disease, the sensitization setup, first from skin exposure and then lung exposure, primarily risk to the ultrafine high particle number. So there's a few, I think, that have not muted their mic, and if you haven't, please do so now. So Mike, without further ado, I'll let you take the lead.
Okay, thanks, Kathy. As Kathy said, I was, after I retired from NIOSH, I was actually consulting for OSHA, doing these surveys. Because she didn't mention it, I'll mention it now, that Kathy was actually part of this. As was Mark Corbett, who's, I guess, currently still working with Materion, doing consulting work, unless he's retired by now, which is not unusual for people unlike me who can't seem to find a way to retire. I'm principally going to talk about air sampling for this. There was some surface sampling that was done, but I think this talk is going to be long enough to sufficiently bore everybody that I didn't want to go into the surface sampling that we got either, and maybe we'll save that for another time.
So Mike, can you make this full screen for your presentation?
Yes.
Thank you so much.
Okay. These surveys are listed with OSHA as this reference. So they are available, presumably, from OSHA if you request them. If that seems like a long way to go about it, you can send me an email and I'll send you a link to these that I have on my website. This started back when I was at NIOSH, and we were doing our surveys of beryllium facilities, looking for a way to come up with a dose-response relationship. At the time, I was just coming off of a project on diesels and looking at diesel sampling. And so we had a lot of equipment to look at particle number and the count size distributions of materials. And we hauled this stuff around. It was kind of interesting. You can see it sitting there in that picture in the lower left. We put that on a hoist and hoisted it up a couple of stories in the air to do some sampling with it at one point. It's a mere $200,000 worth of equipment, so we weren't scared of dropping it. But these are the size distributions that we were seeing on a count basis for a number of different operations with beryllium. And as you can see, on a count basis, not unpredictably, the particle size distributions are all less than a micrometer in size. That's standard aerosol physics lore, shown here, I think, rather nicely by the fact that we do see nothing on a count basis bigger than a micrometer. So when we're looking at the number of particles in the air, we're looking at particle sizes that are less than a micrometer. Now that becomes a little bit of a problem actually when one wants to do dose. So when we look at the kind of standard measures of particle size selective sampling, this is the problem that we run into. And just as a point of reference, I was on the ACGIH's particle size selective sampling committee that was responsible for coming up and recommending these particular standards. So I'm as guilty as the rest, but I think you'll see that I have a few bones to pick with the ACGIH and with my own committee, which we discussed in detail at the time. But you can see for respirable dust, which technically now could be considered PM4, or for the EPA PM 2.5 criteria, once you get up above about a micrometer, then you're sampling 100% of the material. If you're sampling according to size selective sampling specifications and the instruments that meet them. 100% is not the dose to the lungs. The dose to the lungs, as you'll see here, is that dashed green line. So it's substantially different than the solid green line, and it's even more different than the solid blue line. But the reason why we came up with the kind of size selective sampling criteria that you see goes back quite a ways in industrial hygiene history, back to the days when we were trying to come up with a dose-response relationship for coal mine dust and to prevent coal workers' pneumoconiosis. So as it turns out, when we look at the size distributions of coal mine dust, we don't see the kind of bias that we thought you might see if you were collecting 100% when you should be collecting some fraction of it. And the reason for that is the size selective sampling criteria, the ones, if I can go back for a second, for the respirable dust, actually fit very nicely with the deposition curves in these larger particle sizes. And as it turns out in the coal mines, the size of the dust, the aerodynamic mass median diameters of the dust in the coal mines tends to be in this area where, in fact, the lung deposition curve and the sampling curve overlap. And so because of that, you get pretty decent correlation between what is the respirable dust measurement and what is the alveolar dose. And so not surprisingly, I suppose, you see the ability to come up with a dose-response relationship because, in fact, for the types of samplers sampling coal mine dust and the size of the distribution of the coal mine dust, you have a very good correlation. Again, for the other criteria that we think about all the time, the thoracic, there is, again, not the overlap, and certainly not an overlap in the sub-micrometer size range. The same thing is true, of course, for inhalable. And there are other difficulties that one can run into with the inhalable dust criteria. Because the inhalable dust criteria was really designed for doing coal mine dust sampling in a coal mine. The original work on inhalable sampling, you may know, was done at the Institute for Occupational Medicine in Edinburgh, and was doing that for coal mines. And in a coal mine, you have a well-mixed atmosphere. And also a fairly steady wind speed coming from one direction because you're standing essentially in a ventilation tube. But when we look at deposition versus the penetration criteria. So let me go back just a half step and talk about the size selective sampling committee. The folks that were on it were, in fact, other than myself, fairly notable in the field. And these were the people who had done a lot of the measures of lung deposition and lung penetration. And of course, at the time, they had selected the nylon cyclone, and there's a history behind that. Since I come from New York University, which is where that work was originally done, I kind of know the history, but we don't have time for that today. But suffice it to say that it was lying around on the shelf and fit nicely with what we would call penetration into the lung. Penetration is different than deposition. Penetration is actually the ability of a particle to reach an area of the lung, but not necessarily deposit there. So it's different than deposition. Deposition requires penetration, but then it requires more mechanisms going on in that to assure that the dust actually deposits and adds to the dose. So deposition is dose, penetration is just exposure. So the exposure to the lung has to occur, obviously, to get deposition, but then the deposition is some fractional function of the penetration. And so the actual size selective sampling criteria are really set to match penetration of dust to the lungs. And that was how the committee got around not recommending deposition criteria, with one minor exception. So there is a monograph that the ACGIH put out on this, and all of the size selective sampling criteria that you're familiar with, inhalable, the thoracic, and the respirable dust criteria are in there. But in fact, there's one chapter on deposition of particles, and particularly for the deposition of particles that we would call ultrafine. Ultrafines are those less than 1/10 of a micrometer in size. And so there is a criteria called the deposited submicrometer particulate criteria that is meant to handle these deposition-based standards for the lung, particularly for ultrafine particles. And this is just showing you the relationship between the size distribution of dust and the amount of bias that you have between the inhalable penetration criteria and the deposited submicrometer particulate criteria. So for certain particle sizes, you can be off by about 6-fold in the dose. That makes a pretty big difference. You can, if you look at the criteria for deposition and breathing rates, there's a difference between whether you're working or resting, but the bias between working and resting deposition rates is far dwarfed by the bias between deposition and penetration measurements. So penetration, the standard criteria that we think of for size selective sampling, does not do well for these smaller particle sizes. As part of that, then, part of the research that we were doing, actually mostly for the diesel particulate, we looked at a way of sampling these small particle sizes. And also, as I said, if you're looking at smaller particle sizes, the majority of the small particles are going to be less than 1/10 of a micrometer in size that deposit in the lung. And that's on a number basis. If you, there's plenty of it, because I have lots of members of the European community on this call. You know, I give you kudos for having done a lot of this work. Most of the diesel research and the diesel toxicology research has really been done in Europe, and well recognized, I think, in Europe for its validity. And so we see dose response relationships for diesel with particle number, because the diesel particulate tends to be this ultrafine, less than 10th micrometer size. And so the way we came up with doing sampling for these ultrafine particles was to use a condensation particle counter. TSI makes one that they call the P-track, works very nicely for doing that. And we came up with a size selective sampler that we could put in front of that. And it's fairly simple. It's we used a 1 micrometer impactor jet to take out particles bigger than a micrometer, and then sampled those particles less than a micrometer using a track etch polycarbonate filter. Actually 3 track etch polycarbonate filters simply stacked upon one another. We noticed that when we did that and operated them at 2.5 liters per minute, we got a sampling measurement that matched the deposited submicrometer particulate curve. And that you can see here. So both 1 set and 10 set averages match very nicely the deposited submicrometer particulate criteria. And so are measuring, in fact, dose when we use this particular size selective sampler. However, if you were just to take a total measurement of beryllium in areas where there are these ultrafine particles, the beryllium mass does not tend to correlate with the beryllium count. And so you have to, you can't just take a filter and say, well, I'm going to take X% of of the mass that I collected on this filter and use it. You actually have to go in and do the real-time counting with that. And it involves a device that, in fact, will fit in a backpack that a person can wear, as we've used it here. And that was what we did in these surveys for OSHA. So not only did we take the total beryllium mass, we also determined that we would take a deposited submicrometer particulate count of the beryllium. When we did that, we found that in a lot of cases, the deposited fraction stayed relatively stable for a given operation. So in fact, it may be possible, if you do your background work, to come up with something in a particular facility for a particular task that allows you to use mass, but you have to do the background. Now, in saying that, I want to point out that the monograph, the ACGIH monograph on size selective sampling, right up front has a part that virtually everybody ignores, that says if you're going to do size selective sampling, you must first know the size distribution of the material that you're dealing with. Very rarely have I seen any papers that have been published doing size selective sampling that said, oh yeah, before we did our size selective sampling, we determined the size distribution going in. And that's, so you can't just hang a sampler and say, well, we've hung this size selective sampler and that's what the ACGIH says we should use. And so that's what we're using and it's perfectly fine. No, it's not what the ACGIH committee said. And it's not perfectly fine. And you do need to know something about the size distribution, because if you do, then you can do this kind of an analysis without going to the kind of extent that we went through to do it in real time. But if you want something quick, then the method that we used with a P-track in a backpack on a person will work, and it will do it quickly, and it substitutes for knowing the size distribution. Also, of course, when we were looking at sampling in these operations, in many operations, we were working with alloys. Kathy provided this really nice picture of a copper beryllium alloy. The beryllium is not apparently intrinsically combined with the copper. It's occurring perhaps in this vein type architecture. which means that you are in fact getting exposed just to the beryllium, most likely, somewhat diluted by the interspersed copper, which sort of answered a quandary that I think I had among some of my other co-investigators when I first started doing beryllium alloys, as to why the beryllium alloy would be as toxic as the beryllium, or seem to be as toxic as the native beryllium, elemental beryllium that we had sampled in other locations. This probably has something to do with that answer. So because of that, when we wanted to look at the beryllium number of particles in the atmosphere, what we did was we took a mass sample and then did the analysis on the mass sample. It's virtually impossible to do an analysis on a particle by particle basis for beryllium. But we had to choose exactly how we were going to handle a mixture, particularly in any case where the beryllium was not 100% of the sample that we were sampling. So we could say that each one of the particles, then, let's say we found that the beryllium mass was 50% of the total mass. So you could say, well, that mass was divided up half and half in a given particle, or that half of the particles we sampled were beryllium and the other half contained no beryllium. The way we chose to represent this in the tables that I'm going to be showing you was as B, where if it was 50%, we took just 50% of the number of particles that were there and said that 50% is total beryllium. However, if you want to have what the maximum possible exposure could be, then you would simply assign the beryllium to some to this A sort of version, and then the dose would simply be the total number of particles in the atmosphere, since we would then be saying all of those particles contain beryllium, even though it's only a 50% mixture. And as you saw in the previous slide, where the beryllium did not take up, obviously, the entire surface area. So there's a question about surface availability that comes in that could say, well, the numbers that I'm about to show you could be slanted one way or the other towards this, but I've tried to provide in each case what we found, what the percent beryllium was that we found on a mass basis. And then I've applied that to the total count that we've come up with. Stepping back one step again, I want to repeat, because this committee has probably heard me talk about this before, that the reason why we're interested in the number of beryllium particles was when we did those size distributions in that first slide that I showed you, we then were able to count, knowing the beryllium particle number. We were able to count the dose in terms of the number of beryllium particles in the atmosphere. And it seemed to compare with the risk of chronic beryllium disease. And we believed that was the case because we thought that sensitization was occurring through the skin. And when sensitized, then in the lungs, it was a blind walk by the macrophage as to what the risk of it running into a beryllium particle was, since the macrophage was already primed to look for beryllium from having the body be sensitized through exposure in the skin. If you follow that. So on to the actual data. The first shop we went to was an aluminum beryllium metal machining plant. So these were high tolerance aluminum, beryllium, and aluminum beryllium alloys, as well as occasionally other metals that they might use. There were 11 full-time employees and 5 major machining centers in this facility with the kind of standard machining equipment, computer-operated machining equipment that was being done. The nice thing about the plant was that all of the machining equipment was enclosed and automated. But after machining, the workers occasionally performed deburring on certain products as a manual process. But they were using specialized ventilation controls during this. There was also a strict glove policy in place requiring the use of impermeable gloves. Now, in all of these OSHA scheduled surveys, we did not do any measures of beryllium sensitization or to try to determine the incidence of chronic beryllium disease, or actually prevalence, I suppose, of chronic beryllium disease in this case. And you can see, based on this, that most of the processes, in fact, resulted in no detectable exposure. We were able to measure total dust so that we could get a % deposition based upon the particle size that we were looking at. That's this last column over. See that? So the % deposition varied somewhat, as you can see, from a low of 38% to a high of 62%. In most cases where we found the dust, it did not contain beryllium. It was below the detectable level, except for machinist number 3, who, for reasons I'm not sure that I can completely explain, although our suspicion at the time was that they were opening up the equipment a little too quickly, and he was also actually the one doing the deburring operations. So their ventilation controls were perhaps not quite up to snuff. But again, the micrograms per cubic meter of beryllium that he was exposed to was 0.11, which should be good for the kind of standard that OSHA was considering at the time. And then when we looked at the deposited submicrometer particulate beryllium number concentration, which is particles per cc, his was 15. Based upon the analyses we had been doing in the beryllium study at NIOSH, the limit would likely be around 1 beryllium particle per cc. In a sense, if our hypotheses about it being a number concentration rather than a mass concentration are correct, and if these 2 big ifs, if was that a question? I'm sorry. Okay. And if in fact, it was the number of particles in the lung that a macrophage blind walk might encounter that would cause the disease, then in fact, this machinist would have been overexposed for the number. Again, that's presuming that they're sensitized, which they may not be, because the actual surfaces of the plant were fairly clean. Though I don't have that up to go into. That's a whole other set of slides. Second plant we looked at was essentially a recycling plant, beryllium recovery. A lot of copper beryllium alloys really in this plant. There were about 75 employed at the location that we visited that were exposed to beryllium. The amount of beryllium that they were exposed to on a mass basis was not extraordinarily high. The highest one was 0.5 micrograms per cubic meter of beryllium, which would be above what the standard I think OSHA was considering of 0.2. And But then on the deposited submicrometer particulate count of beryllium, again, we get some fairly high numbers for this, 11.34, for example, in one case. And again, the percent deposition fluctuates about one-fold or twofold, from a low of 40% to a high of about 77%. So we're looking at a lot of mechanical processes in this plant. The mill blending, thermal reduction, melting, and shredding mills were all operations that we think have the potential for exposures. And so the other point that I want to make in this talk is that if you have these operations in your various locales, these are things that you need to be aware of. And if you're going to go looking for where you might have chronic beryllium disease, these operations that we're talking about here have the potential for showing that up. So a beryllium recovery plant might be someplace you'd want to start looking. Beryllium ceramics plant. Again, this is beryllium oxide in a ceramic powder form. And this plant was not operating at full capacity, and only about 10% of their capacity at the time. And not all of the processes that we know they could do were being done during the sampling period that we were there. And so I think that may have resulted in the total exposures that we were seeing, the total mass exposures, 0.1 and 0.1, and then non-detect for the other three, to be as low as they were. So this may not be a good indicator of what a ceramics operation is likely to have in terms of their exposures. Nevertheless, again, there were deposited submicrometer beryllium counts that were well above the 1 particle per cc. And again, these tended to be smaller particle sizes, so that the percent deposition for these ultrafine particles ranged from actually a smaller range, but up to about 87%. Probably the largest plant, I think, in terms of the number of operations being done was a beryllium and aluminum beryllium metal alloy machining and fabrication plant. I don't want to give too much away about the plant, but you've seen in the news some of the stuff that they were making recently. Components there were mostly for, when we were there, they were making them for aerospace applications. 110 workers, a very busy plant, lots of things going on, particularly a lapping operation, which was working on fairly large pieces of beryllium. So they make really large, multiple meters long beryllium products. So it offered us a fairly broad look into the range of possible exposures here. So I think that Plant 4 is notable for that. And so you can see that where you are not sampling for chronic beryllium disease, and this plant had issues with chronic beryllium disease historically, you might still have exposures that will result in disease. And so again, this tells you that there's a huge range of particle sizes, which means that just going in and just taking a total beryllium mass measurement is not necessarily going to be the most accurate thing for dose determination that you might do. That's even not allowing for the number hypothesis, number exposure hypothesis, but that the mass beryllium dose is going to fluctuate probably quite severely for this kind of an operation, and severely for this kind of operation because there are just a multitude of different kinds of devices and different kinds of jobs being done. Dental laboratory. There was one person, one regular employee in the dental laboratory. The dental laboratory was working with, I think it was nickel beryllium alloys for dental appliances. The employee, after I did the evaluation in this facility, actually applied for and got compensation for chronic beryllium disease. So if you look at what the exposures are, again, 0.08 micrograms per cubic meter of nickel beryllium alloy, you would think, oh, this probably is not going to be a problem. But in fact, there was really no cleanup of surfaces. And so the chance that this individual was going to get sensitized was probably pretty high. And so the chance that they would then develop beryllium disease based on our estimate of an overexposure being 1 particle per cc, and they were at almost 5. That tells you that there's something to be concerned about when you look at this. And there were no special measures taken to keep the beryllium in place. So the person was going out into the hallways, walking around with the lab coat on, in an area, in this case, where they were in a health sciences school and a school of dentistry, actually, and contaminating the area. Copper beryllium alloy stamping plant. So I thought that this was one of the most interesting ones, actually. And particularly in terms of looking at the whole hypothesis of sensitization being related to skin exposure. Because in this particular plant, although they've never done any surveillance for beryllium disease in the plant, we had people who were working on a lot of beryllium, mostly copper beryllium, in stamping and forming machines. Stamping and forming machines tend not to produce a lot of dust in the atmosphere. However, because they are handling the copper beryllium alloys, they do get copper beryllium on their skin. And so one would expect, if the skin hypothesis is true, that a copper beryllium alloy stamping plant would probably have a fair amount of sensitization, but very little disease. So there were 22 workers in there, but no one who was complaining about lung function loss. So they decided that there was probably not a problem. And in fact, that may well have been the case, that they may have been sensitized, but sensitization without air exposure into the lungs probably does not result in chronic beryllium disease. And a stamping plant might be a place to show that. And so if any of you have access to these kinds of facilities and can talk them into doing examinations, that would be interesting to see the outcome of that.
Mike.
Yeah.
Quick question. This is Ted Knudsen.
Yes.
I'm looking at the percent deposition numbers and for each of the operations and activities. and then all the data is less than. How did we get the percent deposition with less than numbers?
Okay, so we're looking for the percent deposition. We're looking at the particle size distribution of the total dust. Right? So that this doesn't tell you what the total dust levels were.
Oh, okay. All right. Thank you.
Yeah, and that was the point I was trying to make. Thank you for bringing it out again, though, because what we're looking at is percent deposition based upon the total size. Once we know that percent deposition, then we applied the percent beryllium we could see to whatever the count was of total count in the atmosphere. And so, of course, if all of these, then because there is no beryllium in it, or it's less than the detectable limit of beryllium that we could do in this plan, all we can say is it's less than this number, which is the minimum we could look at. So we could obviously count more particles out there, but they weren't beryllium. And so this sort of comes up zero, but it's because you have to do those calculations. So yeah, thank you for bringing that out again, because it's a point I wanted to really emphasize as well.
All right. Thank you.
You bet. Copper beryllium casting plant. So the interesting thing about a casting operation is there's a lot of graphite for really good characterize any of these places as mom and pop operation. This casting plant. If you wanted to know whether they had sequestered the beryllium into an area, all you had where the actual casting was going, and it wasn't getting in the rest of the shop, all you had to do was touch the furniture and come up with all of the graphite that was on everything. So it was kind of an indicator, if we need it, that in certain operations like this, the beryllium is going to probably be found everywhere. Certainly if the graphite is found everywhere, no one would think maybe the beryllium is going to be found everywhere. And so in this operation, we were really felt that we had to tell them that they really needed to clean the place up for their own safety and well-being, perhaps. That might be something that could be a problem. And their exposures, particularly the deposited submicrometer beryllium exposures, were high enough, and certainly so was the mass of beryllium, particularly for the furnace operator, but really for everybody else, it's an order of magnitude higher, at least, than we've seen, maybe 2 or 3 orders of magnitude higher than we've seen in the other locations. So this was, it was a mom and pop operation, and you'd expect, though, that they're doing it and they're making their own money from it, and you can't say, well, you shouldn't be doing this because that was their income. But we tried to make the point that really they needed to sort of enclose the area where the furnace was and the operations, and then have a change out into areas where the rest of the people, there was one other person working out a secretarial kind of job, and she was being exposed just probably close to as much as everybody else. So plant 8 was, our last plant was a non-ferrous forging and machining plant. So there was a mixture of different kinds of dusts here, but some of it was beryllium copper. And the forklift operator, interestingly enough, was the one with the highest exposure on a mass basis. Unfortunately, in the time that we had with him, he did not want to wear the device that we had, but he would wear just a plain old total dust sampler, and I can see why. He was operating the forklift, and he didn't want to have this satchel of stuff around with him and in the way of him sitting wherever. But again, we saw some fairly high levels, so it's possible, certainly in terms of the micrograms per cubic meter, the mass exposure, it's certainly possible that one could predict there was going to be potential for beryllium exposure sufficient to cause beryllium disease in this operation. So another plant to be looking at are these forging and machining plants, because there are a lot of energy going into this with forging operations, hammer forging, those kinds of things. And so it's not surprising that the exposures were so high. The interesting thing, of course, was that the hammer mill operator, we were able to sample a couple of days. And on the first day, he was at 58.6. On the second day, he was at 0.3. But of course, he was not terribly active the second day. So his exposure fluctuated fairly largely. But in terms of the number of beryllium particles, the hammer mill operator was the highest. I suspect the forklift operator, based on the mass numbers, would probably have been high on the particle number concentration as well. And in this plant, the skin exposures were likely, as I recall, fairly high because we were looking at surface concentrations. So again, an non-ferrous forging and machining plant, if you're going to go looking for possible chronic beryllium disease operations or chronic beryllium disease places, are folks in places where the operation is likely to result in something. This would be it. From that, there are some lessons learned, particularly for this group, I think, that number one, the knowledge of the particle size distribution is probably well warranted for comparison of sampling methods, because there is this hypothesis that beryllium number may predict chronic beryllium disease in the face of prior sensitization. Then getting a handle on the size distribution of the materials that are being sampled would be warranted, I think. You don't have to do it every single day. I think one of the other, although I didn't put the lessons learned in the lessons learned, is I think for a lot of these operations, size distribution does not actually change very much on a day-to-day basis. That once you determine the particle size distribution, unless you make some big change in the operation itself, you're likely to see the same thing over and over again. And because I've done sampling in a number of different industries for a number of different projects, not simply beryllium, that seems to be borne out, that if we go into a place today and we come back in a month, we're likely to find the same size distribution again. So once you've established that, gone through the extra trouble of establishing, you can then go back and determine dose. And that's important, not just for beryllium, but in fact, for any lung exposure. So the lesson learned is that dose is ultimately important, just in theory, if not in actual practice, but in actual practice, we think so too. And the dose is not provided equally or correctly by all size selective sampling devices. So just because the nylon cyclone worked for coal dust in the United States doesn't mean the nylon cyclone is going to work for wood dust, say. I just reviewed an article in which they were trying to use nylon cyclone for wood dust. That's a whole other kettle of fish. Also, the biologically available portion of beryllium can't be readily assumed. And so this is one of those areas that I think it would be interesting to do more actual research on and look at what is the surface properties of the material that we're sampling. Mark Hoover, who was my colleague at NIOSH and before that, really well known at Lovelace for doing work with beryllium there, found that certain operations that produced greater surface area per unit mass seem to be much more toxic, seem to produce much more disease. And so surface is really important. And in fact, sampling methods perhaps that are looking at the biologically available surface area in real time would be warranted. And Chris, that's the paper I'm going to be sending in for the Beyond. We've got it. We think we've got a method for doing that. So there does not appear to be a direct correlation between mass and count for beryllium exposure throughout the various beryllium industries, but with the major caveat that once you've done the size distribution sampling, in fact, you can converse mass to count or count to mass, and be able to rely on that probably pretty well. But you have to have your own conversion factor for doing that, which is cumbersome perhaps, but really should be done for anything out there that requires size selective sampling. So it's not really asking for something that we haven't for years. Actually, the monograph that I'm talking about is about 25 years old, I think. So we've been talking about it for the last 25 years. And people have paid little attention to it, given it not much more than lip service. So, and of course, the final lesson learned is that the levels of exposure, if they're not backed up by proper medical and environmental surveillance, should be sufficient to result in measurable disease outcome rates for many of the beryllium industries we looked at here. So it's really important to do the proper medical and environmental surveillance. And in fact, if you just start out with doing the proper environmental surveillance, you may save yourself a whole lot of headaches in the future. And I provided the references for the slides that we've seen here. This work was done with the assistance of Mark Corbett, with Kathy, and with my colleague at OSHA, Michael Seymour. Questions?
Okay. Are there any questions from the audience? Please unmute your mic and ask Mike the questions.
Hi, this is Ted Knudsen.
Yeah, Ted.
Well, quick comment first. Yeah, Mark Corbett is alive and well in Toledo. He is still doing some work for Materion off and on, even at some of the work at Elmore, but he just recently joined Cardinal Consulting, a consulting firm in the Toledo area. So he's not doing his own thing anymore. He's working for them again. So I think
Oh, good.
he'll be expanding his outlook on things. Beryllium won't be the only thing he's looking at.
Good. Well, tell him I said hi.
I will.
And actually, while I have you on the phone, we'd like to come up with I have a couple of students who would love to tour.
Sure.
Okay.
Facility?
Yeah.
Yeah, we can arrange that.
All right. I'll email you.
Okay. The one question I had, and thank you for the information. I remember all this when we were going through this back in the early 2000s, and it was really, really promising, and we all said, okay, can we do this? Can we utilize this in some fashion? And then as we've gone through this process, all the quote unquote safe levels that have been defined, or at least from a regulatory perspective, have been using a completely different methodology to identify what is correct. The EU were using, ultimately 200 micrograms per cubic meter as an inhalable fraction. OSHA is using 200 nanograms per cubic meter as a total fraction. How do these numbers, have you gone through the calculations or the evaluation to see how they kind of relate to those type of OELs now that we're seeing, and the methodology that we're at least determining compliance at this point?
Yes. So the answer to your question is my aerosols course. But let me see if I can distill it down to something. So it's still really, really important. And the size selective sampling committee that put together that monograph were the top of the tops. I don't know how I got on it, but they were the top of the tops in this field. And basically we all agreed that the biggest thing to do is to always know the size distribution you're working with. If you know the size distribution, you can pretty well and actually pretty reliably estimate dose. And you should get to dose, regardless of how you get to dose with whatever you're looking at. So if you're taking an inhalable sampler, then find what the size distribution is that you're getting coming in through that inhalable sampler. If you're taking a respirable dust sample, know what the size distribution is that you're taking in with that. And then, in fact, you can come up with a correction factor for all of that. You can do it after the fact, you can do it before the fact. And that helps you. The other point that I didn't really make in this, I'm glad you brought this up because I'll make it now, is that my own personal belief, this does not represent OSHA, NIOSH, or anybody else. My own personal belief is that if you control surface contamination, you don't have to worry about the dose. That I think for most of the operations now, that one plant where the dust levels were really, really high, that might be the exception. But for most plants and operations where people have, for now at least, known for a while that they need to keep their air levels down, if they can keep the surface exposure, and particularly the skin exposure, directly. So, there are two ways you can go about doing that. You can measure, take wipes of the areas that people are working on, and then take wipes, things like their hands, and look at surface contamination that way. And I think that if you control surface contamination, you control the problem.
Yeah, and I would agree. Part of our worker protection model is certainly housekeeping, and keeping those surfaces clean so they're not, for a variety of reasons. One, the material doesn't get drained into the air, and skin contact is minimized by keeping everything clean at that point. Now, foundries are inherently dirty, but they can be contained and controlled appropriately with the appropriate controls. But
right,
more of a challenge than other situations.
Yeah, unquestionably. I mean, doing some of this is going to be a challenge. It's going to take some creativity and a little imagination. But I think it's all within the realm of the abilities of the people that are dealing with this stuff.
Well, and to address one of the other concerns you had was certainly with the new OSHA beryllium standard, if you do have situations where you're at or above the permissible exposure limit, medical surveillance is going to be required. So there are situations you will now get to see sensitization rates and CBD rates based on exposures above the PEL. So
but necessarily in Europe, and if I were talking strictly to a U.S. audience, I probably wouldn't underline that. But I know who I'm talking to here, and I know what they're up against, and so I want to emphasize that you want to do medical surveillance. You really, until
Right.
you get a feel.
Right, recommended to do on all the Beryllium workers, including the administrative staff. I think what you did on many of these studies, especially the NIOSH studies, and at times did find administrative staff have sensitization and disease. Okay, are they, and go ahead, Mike.
We know we were in a couple of plants where folks that were administrative staff and did not have jobs in the plant itself still showed up at least sensitized, and in I think 1 or 2 cases perhaps they had disease as well. But I think that, again, because the workers were in and out of areas and they were contaminating areas that were not in the plant.
Right.
Just think of the exposure to the graphite.
Workers coming with the contaminated clothing.
Yeah.
As well. Okay, are there any other comments, questions for Mike? Okay, if not, I think that I'm going to introduce Chris Dorn. So let's see what happened here. And so we have a pretty large audience. So we have 30 people here. So Chris Dorn used to work for Materion for 30 years, and he has a lot of experience of what industries are involved with making beryllium containing components. So I'm going to share my screen and just give you like 1 or 2 slides to give you a feel for the market and also, you know, the industry. So this is a beryllium market by the volume of the material. So you can tell here that the industrial components, the industrial components and the electronics industry make up 50% of the volume of beryllium containing materials. And that the aerospace and defense is not minor, but it's not the major one. And then you also see the demand by region. So the United States is high, but also Europe and Asia kind of equal with each other. Then just another slide, you know, pie chart with the dominant markets being industrial, consumer electronics, and automotive electronics. And so, Chris, can you comment on your experience with the modification, the changes in the beryllium industry over, say, the last 10 or 20 years?
Thanks, Kat. Yeah, I think a couple of things just to, you know, to try to keep things a little bit in perspective. I mean, these days, I work at the UK AEA, so and that's the home of a fusion research reactor that has, you know, a ton or 2 of beryllium in the form of tiles, beryllium metal in the form of tiles. And you know, I spent my career with Materion and subsequently, you know, mainly working with beryllium metal. But, you know, as Mike showed in his presentation, and something that's really important to understand is that, you know, even though that was the main point of my career, that's what I worked on, and that's what was important to me and that I knew the most about and all of that. You know, in fact, it's only a small amount of the beryllium that's made every year that actually goes into making beryllium metal or high beryllium content materials. Most of what's out there are these beryllium, we call them beryllium alloys, but in fact they're alloys of other things because they're more copper alloys or nickel alloys or aluminum alloys because they actually only contain a very small amount of beryllium. but that's actually where all of the that's where most of the beryllium really goes. The alloy business is a way bigger business. The consumer electronics you see there, automotive, industrial, all that stuff, that's mainly copper beryllium or other beryllium containing alloys. And beryllium metal goes into the defense, a little bit into medical, and the nuclear stuff, like the fusion research and also fission research reactors. But it's really, I think that that beryllium containing materials are a lot more ubiquitous than what you might think. We always think of beryllium as being this, rare and expensive thing, but which to some extent it sort of is. But the truth of the matter is that it actually finds its way in small quantities into all kinds of stuff. And so beryllium oxide ceramics and copper beryllium alloys, nickel beryllium alloys, those are the ones that find their way into your laptop, your cell phone, your automobile, stuff like that. And so so it's important to understand, I think, that that there is a difference there. And when we talk about beryllium, when I say we, where I work and the part of the business that I've spent my career in, we're mainly talking about beryllium metal, but in fact, that's really only sort of the tip of the iceberg when it comes to, where beryllium is being used. So I think it's important to understand that.
Well, thanks, Chris. And I think I want to point out that, you can go directly from using the pebbles, which I think is beryllium hydroxide, to manufacturing copper beryllium. It doesn't have to go into beryllium metal first. And, NGK used to be the leader manufacturer of copper beryllium, but can you comment on are there other facilities that are making copper beryllium?
Well, I mean, I guess what I would say is, so, I'm not really an expert on the alloy side of things, but what I do know is that, back in the days when I first joined the industry, so we're talking 1987, at that time, there were only just a handful of companies that were really, Brush, as Materion was called back in those days, was one of the primary ones, and of course NGK, and NGK actually got their beryllium from us, from Brush, and so and at that time, there weren't a lot of producers, but what's happened since that time, in the last 20 years, with the fall of the Soviet Union and therefore the Ulba plant in Kazakhstan,
Mm-hmm.
and then China has become an economic force. I mean, in the 1980s, the Soviet Union and China were not selling beryllium products on the open market, and so back then you could count on one hand basically the major producers and stuff. But today, I mean, my understanding is that now there are dozens of companies in China, for example, alone, that make copper beryllium alloys, for example. And there's a big, Mike touched on it in his presentation, but the recycle side of it. So there's a big recycle market, and there are scrap dealers and things like that. There are some companies, I think, that basically, don't have to make any primary beryllium or even acquire primary beryllium. They can just buy, copper beryllium scrap and recycle it and reprocess it to make new material. So I think that there've been, and again, it's not really my specialty, that area, but from what I've observed and from what I have seen in the time that I've been working, I think there's been a very big change in the alloy market, and the number of companies that are involved in handling the material now.
And I would chime in that Kazakhstan was given funding by the Department of Energy actually to establish the copper beryllium manufacturing at the Olva plant. So I was, Mike was involved in that study as well, that we went to the Olva plant. So Mike, there's a question here by Jackie Morton. I don't know, Jackie, if you want to give your comment now, or if you want me to mention it. Okay, she says, I think there would be valuable to explore the use of biological monitoring for beryllium in many of these workplaces. They've established and published data from aluminum beryllium facility that showed elevated beryllium in urine levels compared to controls. There's also normal urinary beryllium levels available. There are differences between soluble and insoluble beryllium species, but importantly, it can show the exposure from all the routes. And, you know, I know, Jackie, that there have been a lot of evaluations done with urinalysis. I just want to point out that this is not a substitute for using a medical screening test, which is the beryllium lymphocyte proliferation test. But I'll go ahead and have Mike McCawley make some comments on this.
Yeah, thanks, Jackie. That's a good point to bring up. So let me explain something, because I just got a question actually through Kathy this past week about this similar sort of thing. I did some work in the aluminum industry as a consultant, and in aluminum smelting operations, you get a fair amount of beryllium fluoride being generated from the bauxite ore. And in fact, the pot deposits that come off, and that in some plants are just everywhere, I mean, literally ankle deep, contain this beryllium fluoride. And yet, when the aluminum industry went through and did an evaluation, they did not see much beryllium disease using the standard surveillance methods that the US has adopted, which is the BELPT, the beryllium lymphocyte proliferation test. And the thinking is that beryllium fluoride, first and foremost, is highly soluble. And so when you get it in your lungs, it tends not to stay there. And get it in your body, it tends not to stay there. So that you would probably, almost certainly, I think, pick it up in urine. And that would not be necessarily a good indication of risk. However, having said that, I don't think you can get beryllium disease or beryllium sensitization without some partial solubility of the beryllium. So you're kind of in this equilibrium zone where the beryllium has to have mild partial solubility so that there's something there in solution for the immune system to pick up on. And of course, we know that even beryllium metal is mildly soluble, that you can get an ion or two coming off of it. And so in doing the urinalysis, that might not, depending upon what's being worked with, if you've got a lot of soluble beryllium, I would think that the urinalysis is probably not going to be very indicative of the risk of disease, because although actually the aluminum industry said, well, we think we have a case. In looking at it, it looks an awful lot like a disease that most people aren't familiar with, which was acute beryllium disease. And acute beryllium disease certainly seemed to be associated with the beryllium fluoride furnace operations that Materion, formerly Brush, had going. And acute beryllium disease resolves. It's not a chronic condition. All right, Ted, you want to chime in?
Peggy, do you have a question?
Yeah, I did want to chime in. The studies that were done by Taiwo and all in the aluminum industries actually were involved, actually beryllium, not beryllium oxide that was in the kind of the pot room after they got the aluminum out. The bauxite that they got from Jamaica was contaminated with beryllium ore. So they
Right.
had very, very low levels of beryllium in their plant, resulting in very low levels of sensitization and disease. But it should be noted that they did have cases of beryllium sensitization and beryllium disease, even with very low exposures that they got from kind of the leftover remnants of their smelting operation. So it wasn't beryllium fluoride, at least in the American industries that were smelting aluminum to make aluminum. So I just wanted to point that out. And yes, they used beryllium, the beryllium lymphocyte proliferation test to screen all their employees, and actually found a very low rate, which was associated with very low levels of beryllium exposure in the plant.
Yeah, I think that's right. But if you look at all of the beryllium exposures, and without saying too much more, because I was doing this as a consultant to them, but I did most of the sampling that they reported. Those were my environmental samples, and there was sufficient beryllium there. If you don't discount the beryllium fluoride, there were sufficient levels of beryllium there that they should have had rates of chronic beryllium disease probably similar to what we saw in Elmore, because that's what the exposures were. But you're right, there were very low levels of elemental beryllium available, and that might have been the case. But I also, in looking at their description of the disease at the time, it certainly looked like it could have been acute beryllium disease rather than chronic.
They didn't have any acute beryllium disease. They were all they were classic chronic beryllium disease there. I don't know if that was if you were the plant that was done, evaluated by Taiwo and all.
No, but he and I were in on the same conversations. So we worked in parallel at that time.
Okay, well, that paper is very interesting to show that low levels of beryllium exposure in a plant still result in sensitization and disease. So
right. No, I don't disagree with you.
The importance of using medical surveillance with the beryllium lymphocyte proliferation test or an equivalent to determine who has become sensitized.
Yeah, absolutely. No question about that. But it's of the insoluble beryllium, I think, that we're talking about, because a lot of the soluble beryllium exposure levels weren't published.
Okay, so Jackie Morton has a comment. Jackie, can you go ahead?
Sure. It was just to reiterate what I've been saying in the chat, and that's that it's a measurement of exposure. When you measure it in urine, it's not going to stop the disease. The only way it will stop being sensitized to it is by reducing exposure. If you can show that your levels in urine are low, then you're controlling exposure better.
No, not necessarily, because and that was the point that I was trying to make. So the beryllium that's probably the most lethal, if you want, is that's only very slightly soluble. If it's really very, very soluble, I don't think it produces anything.
I don't think enough studies have been done to show that.
I think that's true. But
insoluble metals can be detected in urine, different to beryllium, and we can still detect differences between controls and workers working with insoluble urine. And you see this with nickel.
I think if you're comparing apples to apples, so if you're in a plant where it's insoluble beryllium, that you don't have this mixture of beryllium element or beryllium compounds that are soluble, you have just beryllium, then yeah, comparing apples to apples, if you have high levels of beryllium in the air, that's relatively insoluble. And the levels of beryllium in urine in that case probably are going to be proportional to the exposure in the air, I would think. But again, you have to watch for the soluble beryllium, because that's going to have, I'm pretty sure the toxicokinetics of that are going to say you're going to see it in the urine at very high levels that would lead you to believe that they're in much worse condition, when that's not necessarily the case. That what you have to do, as Peggy was saying, is be aware of what is the insoluble beryllium levels.
I'm sure that, I mean, there are precedents set where you have different exposure limits depending upon, or different guidance values in a biological sample depending upon the solubility. So it might be the case that you would have different tolerable ranges for different solubilities of compound.
Yeah, I think that's exactly correct. Yeah.
So if I could ask Mike or the others in the audience to comment to countries that have services to provide to worker populations. If you had a choice of developing a test for beryllium urinalysis or for developing a test for the lymphocyte proliferation test, which one would you choose? Mike, do you have any comment on that? Or can you hear me?
I just noticed Beth had put up her hand, so.
Oh, okay. Yeah. Beth?
Hello. So for us, what we're finding is when we do urinary analysis, if we come across an above 90th percentile, we retest under the same conditions, and universally so far we've come back with a completely different dosage on the urinary analysis result, and it's almost exclusively lower. So it doesn't seem to us, and again, we're not doing it regularly enough at the moment to get lots of results, but it doesn't seem to us to be a particularly accurate method of exposure, because as you were saying, Mike, if it's soluble beryllium, it could be from another source, and it doesn't seem that the machinists that are working in the area, it doesn't seem to be matching with what they're doing. So like I said, we repeat the test, exactly the same conditions, we come back with a completely different analysis result.
Thanks, Beth. There's also Joanne Gill has her hand raised.
Hello.
Hi, Jill.
Hi. A couple of notes to make. One of them is that in the UK, you're meant to not opt for an invasive method if you have other methods that offer equivalency or satisfy the criteria for health surveillance and other measures within your worker program. So that is one sticking point. The other one, we have looked at biological monitoring, and some of the internal and external papers that I've looked at lead me to believe that really you need to have an exposure over the current occupational exposure limit of the 2 micrograms per meter cubed to start to see something of particular consequence. But when you've got your biological monitoring program in place, you need to really know what your normal is for your individual profile to understand their own metabolic uptake and excretion levels, to demonstrate that you have a deviation and to establish the standard deviations from those deviations, and to put that program into place. And that is something that you can use in synergy with your personal exposure program and your worker exposure program. We have done some studies, and actually looking at the German levels and looking at some of the data which Jackie's produced and the equipment, it's also very useful to potentially broaden it out from beryllium to other metals as well. But actually the interesting thing there is, I think for the purposes of the studies that we've seen so far, I'd prefer to be basing that at the 90th percentile, not the 95th. And actually, we did have consistently reproducible values that we looked at. But I would take with caution how you exercise and how you implement a biological monitoring program. For me, the use in application will be you're looking at a body burden of throughput and potential some retention, and comparing that to your inhalation limits as well. So I don't think it could be used in isolation as part of that overview picture. Thank you.
Yeah.
Thanks, Joe.
I can just comment back on it. The toxicokinetics of beryllium, of soluble beryllium versus mildly soluble beryllium, I don't think have been well documented or well understood, which was, I think, the point we were making before. So yeah, you just underlined, I think, one of the difficulties with this. But if you can, if somebody can establish, in fact, that they've got a baseline and that they can use that baseline to give them something that's sensitive enough to see when they've got an overexposure, that it'd be interesting to follow up on that and to hear reports of it.
Okay, so I can take one more question, and it's approaching an hour and a half. So Ted, you have your hand raised.
Thank you. Well, just to answer Jackie's question, I think the biologic monitoring has some value in the process, and especially as we're looking at uncontrolled exposures, whether they be inhalation, ingestion, through the skin, et cetera. You're going to see some of that information collected on a urinalysis. Now, whether or not you can define it in any sensitization or risk of CBD is a different subject. Obviously, the BLPT will define sensitization, and as we all kind of agree, you need to be sensitized to beryllium, and then of course have lung burden in order to have CBD. So I think from a Materion perspective, I think we would suggest that the BLPT would be a better methodology to define risk, at least with exposure to beryllium, at least airborne exposure to beryllium. But that urinalysis will have value in trying to determine if there's exposures that we're not aware of through all routes at this point. So it does have value. Just a matter of, can we correlate everything and make it defined enough that you can utilize it in that area.
Thanks, Ted. Okay, I think that it's time for us to close the meeting. I want to thank everyone for participating, and I will be posting the recording of this on the BSI web or YouTube link. And if anybody has any questions also for me or Mike McCawley, I'm sure or Chris Dorn, they would be more than happy to answer your questions. So with that, I'm going to close the meeting since it's getting quite late, and I appreciate all your participation. So take care and have a good evening or a good day. Thanks, guys.